start here. Okay, so as people are filtering in here, I'll try to give you a brief idea of what this is all about. And I'll explain what this thing is too in a bit. I don't know if you noticed this is on the sleeve of the shirt. Well, when I went to Sprint, I started observing some really interesting things, and after being there a while, I was trying to understand what was going on in the internet in general. And what I learned was I started getting this growing feeling that there was a lot of complexity being built into things and not much analysis of that. And that's where I started with all of this. And all of these people up here have their expertise in different areas of this. And I'm also, before I get going, I just wanted to say I wanted to get some more people from the MPLS community, but the unfortunate thing is that the MPLS 2000 got scheduled over the top of us. So I couldn't get some of my friends like Yakov and Karidi to come out and talk to us. So hopefully if we do this again, we'll get them. So this is where these slides are, and let's just try this. Okay, so here's what I'm going to do. I'm going to sort of give an introduction and a few observations. Then we're going to do panelist presentation and discussions, and then at the end we're going to do question and answer. When I did this with the BGP thing, whenever that was, I tried to hold the question and answer part of it to the end, and it didn't work. So I want to try it again. And if it doesn't work this time, I won't try it again. But basically, if you have questions, try to hold them to the end. I have 20 minutes for you to ask whatever you'd like. So here we go. So you might ask, what is this panel about? Because I did. And what I came up with is this. There's growing complexity in the internet technology, and that is not in and of itself bad, but it's one of these things that we really need to start looking at a little bit more closely. There are a lot of implications of this, both to operability, CapEx, OpEx, all of that stuff. So the goal that I set out to kind of try to hit here is I would like to try to start socializing people to the understanding of what this complexity is, where it's coming from, what are the issues for all of us. Because I think that field itself is just growing, and it's a pretty exciting and dynamic field right now. And the internet's an object that's used frequently by people who are studying dynamical systems. And what I'm talking about is both in what we build and what we write. So I had an idea that maybe we should just change the name of this thing to Wake Up and Smell the Complexity, because it seems to be everywhere. And that's the draft that Randy and I have that sort of tries to outline some of the initial ideas that we had in this area. So, okay, so then I'll talk a little bit about the discussion format. Okay, so here's what I want to do. This is a little bit experimental, so I hope it works. This is the format I want to do. I'm going to do the introduction, so that's what I'm doing now. And then I want to give each presenter 7 or whatever they can do their presentation, and then have a little bit of discussion amongst the panelists, because they all have interesting ideas on these things. So I hope that works. And then at the end, we'll have the 20 minutes for Q&A. So these are the panelists. Well, this is me. And then we have Randy. He's going to talk about the differences between telco and ISP architectures. Vijay, Dave Ward, Thomas, and Lisa. And then we'll do the question and answer. So here's my part of it. So what is the complexity, and where is it coming from? What are we concerned about here? Well, there are a lot of sources. But there's nonlinearity inherent in large systems such as the internet that really go to how we design and operate the network. And some really nice recent work in dynamical and nonlinear systems it suggests that highly designed systems, and the internet is usually one of those highly designed systems, are what is being called robust yet fragile. And that does sound like kind of a contradiction, right? Robustness and fragility seem to be on the different ends of the spectrum there. So what does this mean? Well, what we're learning is that basically a system needs some degree of complexity in order to achieve robustness, but it does so at what we hope is an increasing sensitivity to hopefully rare events. So that means that these rare events that occur where you have sensitivity become more and more catastrophic as complexity rises. And the key observation here is that while the system's robustness is bounded, you can get so much reliability out of the system, the complexity isn't. So there's some robustness, complexity, distribution in these systems that is heavy-tailed. And this is what it really means. Let's see if I can see my picture here. Basically, if you go past the point of some maximum value, you can keep building more and more complex systems, but you're going to pay the price of increased sensitivity and cascading failures and things like that. And this citation here is a pretty good place to start if you want to understand this. It's a pretty nice field. So where's this coming from? Well, there are two fairly well-known principles from nonlinear systems theory that play into this. One's called amplification, the other one's coupling, and there's all kinds of nice examples which we'll go through or see a couple of them anyway. So what amplification says is that at large scale, there are nonlinearities that occur at large scale which aren't observed at smaller scales. And one of the ways to think about this is that if you have a really huge network, sometimes even small things are huge and can be stabilized the way a system's output works. So what's an example of this? This is a place where I like to be able to get some interactive thing, but I don't think we have enough time for that. So yeah, in large systems, even small things can be big. So what are examples of this? Well known now is the multiplication of BGP messages across the mesh of the internet. Tim Griffin has some work showing that a small amount of interconnectivity can cause the output of a routing mesh to be significantly more complex than the input. So these are real good examples of amplification. And these are things that we really need to watch out for when we're designing networks. And the draft that we cited has quite a few more examples in it. Oh, and it's interesting too because you see this all the time in nature. It's not really anything specific to the network. So if you look at this and you see Craig and Abba's work and you see well this is really bad because it could take factorial time for BGP to converge. Well, it kind of gets worse. What can happen is this is the Tacoma Narrows Bridge, or it was, and what happened here was there was a linear resonant amplification that occurred when some wind blew down this gorge, and it blew the bridge apart. So it can be worse. Okay, another principle that we need to think about is called coupling, and the idea here is that as these systems get larger, they frequently exhibit increased interdependency between the components. And kind of the way I like to think about this is if you have a really huge system and there are a lot of events occurring, there's just a greater chance any two of them will interact. And again, from the complex systems field, this is has been termed unforeseen feature interaction. Well, it goes in all different kinds of directions, but much of the nonlinearity is due to coupling, and it has horizontal and vertical components. So this is like across, well, I think I have a bullet on this, but basically it's either across layers or between layers, and we know for sure that we get it in both directions just by all of our experience. So one thing you might consider is that layering might be considered harmful. Some examples that we can look at. Well, Van and Selly's work on synchronization of control loops, slow start synchronization, routing updates, that sort of thing. Oh yeah, and so this gives us another clue as to what's going on here, that a lot of these coupling phenomena are closely related to synchronization, and we know that, I hope I have this bullet in here. Yeah, we know that injecting randomness can help us with that. Another way is just to ensure that local changes have local scope. So these are things that are happening in large nonlinear systems like the internet, and we don't really have a way of quantifiably going from what our designs are down to what complexity is costing us, but we're trying. That's what we're doing. So what can we do? Well, what design principles are available to us to control complexity? What do we have? This is the one that I kind of think is operative right now. And you can read it, but basically what it says is that complexity is the mechanism that drives cost. And I think this is Mike Odell. Does anybody really know for sure? I've tried to track that down, but I don't know for sure. All right, so I wanted to just give one more example before I get out of here, if I can find where I was. And this is on 5.9s. Now we heard a little bit about reliability today. 5.9s plays into this in a pretty interesting way, and it's really the idea that you could really get unbounded reliability out of components in the network. I had this thing in here that said optimization considered harmful, but I think Sean Doran objected to that, so I softened it. Arbitrary optimization. And why? Well, because optimization frequently introduces complexity and tighter coupling between components and layers. That's actually what you're doing in large part when you're doing optimization. Oh, and then I have a good quote here from Randy. Best code is no code. That's kind of an optimization. That's sort of like a virus evolution argument, right? All I need is a strand of RNA. But basically the idea here is that, and the implication is that trying to squeeze out efficiency past some point is only going to add complexity, increase nonlinearity, and make for less reliable systems. And in economics, this is called the law of diminishing returns, so we kind of know it pretty well. We just don't apply it that much. But you still might ask, why? Why is 5 nines a myth? Well, here, let's do that then. Well, there's a lot of work that suggests that 80% of unscheduled outages are caused by people and process error. So what this means is you have about a 20% window in which to optimize components. But what happens? How does this optimization occur? Well, basically, generally, you add complexity, which is the root cause of the original 80%, and that effectively narrows the 20% window, because what that does is increases the likelihood that you'll have additional people and process errors, because now you're dealing with a more complex component. So, there's another way to look at this, and this again comes from the complex systems field. The same reason it's hard to get to 5 nines or any arbitrary standard of reliability is characterized in the complex or the dynamical systems area these days as a complexity robustness spiral. And what happens here is you have this complexity which has a set of sensitivities, but in order to address those sensitivities, you add more complexity to the system, which itself has additional sensitivities, and all of a sudden you're spiraling. Okay, so here's a good one. This was the thing, actually I have to thank Lucy for this. She found me a Grateful Dead themed complexity robustness spiral. And you can see what happened. This was the Dead's problem as they got pretty popular after the Wall of Sound was built and all of this other kind of stuff, if you're a Grateful Dead fan. But basically, here, the thing's called an Ouroboros, which means devouring its tail. And again, Chandran gave me a nice URL there. But basically what happens here is, you can see what happened to them. They got greater demand, they needed larger halls, this required more equipment, big organization overhead, more gigs, and then all of a sudden you're back around and now you're spiraling. So this is what happened to them. And it's kind of interesting that this same phenomena is the one we're dealing with when we're trying to get to 5 nines. So as I looked at this, I thought, well, the more things change, more or less, the more they stay the same. And I'll say why in a second, but I just did want to say that a couple of times when I've said this, people have said, well, we don't want to let our router vendors off the hook, and that's definitely the case. We can always do better. But if you look back in history a little bit, there's a pretty classic paper called Some Perspectives on Network Past, Present, and Future from '77. And basically what it says is the Internet's built out of simple components, and the reliability doesn't come from component reliability. I really highly advise reading that paper. It's pretty interesting. So here's the long story short on 5 nines. Basically, while a system like the Internet can reach 5 nines like reliability, or maybe more, it's undesirable and likely impossible, or some version thereof, to try to make any individual component reach an arbitrary reliability standard. And this is why, because of the complexity robustness spiral we get into. So this is my editorial comment before I turn it over to the people you really came to listen to. The current trajectory looks like this to me. We probably need to find ways to control the complexity that we're building right away. And again, this is my opinion, but it's going pretty rapidly in the other direction. And the problem with this is that we could easily cross a complexity barrier that puts fundamental limits on our ability to efficiently scale, or causes the Internet to completely collapse. And I just have a few other things here that could happen. We couldn't make a business out of it. We can't get the performance, or any other number of things. So I was trying to find a complexity metric that we could all understand. So I thought, well, what about the number of IDs submitted prior to the IETF? The last time it was greater than 800. It seemed like a pretty large number. Okay, and that means that we have an abstraction that scales pretty nicely, the internet. But I'm wondering if it, and Sean was really giving me this idea, I wonder if this represents some kind of de-abstraction. We're not really sure. So finally, why are we doing this work? Well, excuse me. The main concern of, I think, many of us is that there might be a critical complexity barrier that's much, much closer than we think. And, oh yeah, of course, as shocking as this may seem to everyone, we need much more data and subsequent analysis of that data if we hope to really understand this at all. So that's kind of my introduction to why we're doing this. And I want to get back to where I was, where all the people are. Okay, here we go. So I guess we're on to Randy now.
Thanks, Dave. The quote is Tony Hoare, by the way, is premature optimization is the root of all evil. I have to figure out how to operate this complex computer. It is a heretical view, and so a sense of humor is required. I'm going to try to wake you up. So, some of my best friends use MPLS, but I don't know that, and I do hope all my competitors use it very heavily. It does have some uses, but I would be very careful. Okay, I'm just going to try to compare the telcos, try to get some lessons from the telcos that we can apply to the internet space. Okay, and first I want to say, can I stand still? The internet does work. It actually does. IP forwarding is just as fast as switching. They're all just one lookup in a table. And in fact, the story today is I hear that there's a case of a significant router vendor where in fact it takes more time to switch on a label. Okay. Actual measurements show QoS is just fine on the backbones due to proper provisioning, and proper provisioning is cheaper than having a layer. Also, QoS is a decision of which packets to drop, and do you get paid to drop packets? Right? I don't. Right? And when I ask my customer, do they want their packets dropped? They say, no, I want you to drop their packets. Right? So, there are reasons the internet is taking over the data world and threatens voice. Okay? Reliability and resiliency are core strengths of the internet. It was designed from them. Our weakness is security. As was the telcos once. Remember the 2600 stuff? Remember? Okay? We all learned. World gets nastier. This is unfortunate. The complexity is one thing. The nastiness is really bad. Okay? IP routing uses good service, switching, blah, blah, blah. IP path alternatives at layer 3 routing, if there's a way to get there in the mesh, it'll get there. MPLS is the telco philosophy of have one backup, maybe two, right? So I know of a major ISP who had 3 almost simultaneous fiber cuts of, I forget, 11, 12 OC48s. And their customers did not notice. Okay, and they're pure layer 3. Good old Mike Odell, we all quote him. The only problem is scaling. I'm going a bit fast, by the way, excuse me, but I didn't find about time until after I'd made the slides. And everything else inherits from that. If we can scale, things must be working. Okay? Complexity is the arch enemy of scaling, and hence of the bottom line. The telco culture in the 70s, to compete with each other, started adding feature. And there are these bags on the sides of switches and boxes and features, 500 features all interacting with each other. And so they built a culture where being able to design in this space didn't cause fear, it showed you're macho. It was cool. I could add this feature and have to have 30,000 people touch 1,900 things, and it may still work. Okay? But look at what it did to the operational costs of the telco network. those people are complaining about a lack of margin and the death of the, how many pennies per minute. ISPs, unlike those years in the telco, were all buying our garbage from the same vendors as the competition is. We don't have hardware, I can't fight you with hardware features because I'm not building the hardware. Okay? So if I can buy it from my vendor, you can buy it from your vendor. So if we start a complexity escalation war, it's like the Cold War, two old men drinking poison to see who dies first. Okay? And our good old RFC 1925, it's sufficient for us, the pigs fly just fine. This does not mean we can afford the fuel costs, and who wants flying pigs anyway? What's the difference in the two networks? In the telco network, voice has very stupid edges. That voice instrument, pick it up, clunk, it's got 4 parts in it, and that's not because of highly scaled integration. You can do it with 4 mechanical parts. A little bit of carbon, and then you've got near piece and so on and so forth. They have a horribly smart core. We have very smart edges, hosts that are very complex with applications that, with a text editor that has a footprint of 7 megabytes. And we have a very stupid caller. All it does is forward little packets, happy packets that just want to get to their destination. Okay? So this means that adding a new internet service over that dumb core means just 2 hosts at the edge colluding, and they've deployed that service, right? A server and a client or peer-to-peer. And 5 more can join them tomorrow, and all of a sudden the World Wide Web takes off, and nobody had to change the routers. People had to buy more circuits because traffic went to hell, but hey, they paid me money for those circuits. Okay. And this was true until NATs, by the way. I have to have my anti-NAT remark. Okay, because all of a sudden we don't have end-to-end, and things can get a little more complex, and adding a new application may mean tunneling through NATs, and we don't want to think about it. Compare that to adding a service to the voice network. You have to touch every switch in the network. And that's expensive. And that's just for one person on one end to talk to the other. So to add a feature, you have to be able to project the sales of a jillion. Experimenting on the voice network isn't done. Experimenting on the internet is done every day. The reliability on the voice network is done by large, central, highly smart things that are in bunkers with batteries that last. The ones in the bottom of the World Trade Center, I think it was a 7 ESS, Tim? 5 ESS stayed up for 3 days after the death. And its problem was it ran out of batteries. Right? Okay. The internet, on the other hand, assumes major component failure. It's a classic case of building reliable systems out of unreliable components. Okay, and it achieves that reliability through redundancy in the protocol. The DNS last week, word servers were seriously attacked. Customers didn't notice. Right? Protocol simply route around it. Okay? Carrier class reliability, those 5 and 6 nines we want. The famous 5 ESS switch regularly hits 5 nines in operation. That's expected, and has hit 6 nines in the field for a year in real sites. We really want that in routers and in other internet boxes. Can we achieve this? Well, maybe we can take a lesson for how the 5 ESS achieved this. Well, the fact is, the 5 ESS has a massive amount of data in it. And what it is that data is denormalized and splattered all over the place. And so there's a supervisory function running around continuously, cleaning up the internal inconsistencies in the data structures, continually. And without this, the 5 ESS crashes in a few hours. Okay? You can't do this on a distributed computation like the global internet. Imagine trying to run something to fix up the routing tables in all the routers all over the internet. It's called routing protocols. Okay? We can't do it that way. There is no lesson here. They didn't have the reliability. They had a lot of cheap labor. Okay? On spreading across layers, they said, hey, it's always possible to, again, 1925, agglutinate multiple separate problems into a single complex interdependent solution. It's a bad idea. Okay? That's why ATM failed. They tried to solve QoS, traffic engineering, everything at once. 1925, every old idea will be proposed again, yes. Okay? Trade-offs across layers are another matter. As Dave said, overlayering can be bad. But, you know, hey, we got DWDM up the yin-yang. Give everybody a slice. Right? It's the same infrastructure. All you got to do is light the optics, which ain't cheap, but it's like everything else, it's falling like fast. Fiber bandwidth is falling Moore's Law or worse. Okay? Maybe we should not increase the L2, L3 costs, and instead, okay? So, to close, this is my heretical approach to operations. This is a little researchy. With enough complexity, we strongly suspect we can operate an approximate internet in polynomial time and dollars. This is being shown, right? We are working on a proof that operating the internet can be made to be NP hard. This will assure all those people of employment. And then we'll just wonder where the margins went. Just like we do in the telco today.
So here's a chance for us to see if we can get one comment out of our panel on something that Randy said. Anybody have a comment? Nobody would even comment on anything Randy said.
I will comment when that talks.
Oh, okay.
I have some counterexamples.
Oh, good. Okay. Well, in that case, VJ.
All I'm going to do is show some data to back up what Randy said. So queue management strategies. Perhaps we're going to solve a problem that may not exist, because I see no reason to pay for gate counts in forwarding engines, especially if you have a good negotiating team, and we do. Especially with all these people willing to sell us below cost, we will try to lock in as much as we can, as quickly as we can. So I'm going to show you some graphs of the ATDN backbone, which is a NOC 192 4-continent backbone. And there's no point in showing any packet loss because it's consistently boringly flatlined at 0. We will show you jitter and the actual traffic. This is not some made-up, double-counted core bisectional bandwidth number. This is the total amount of traffic that comes in on our imports, and this is the total number of traffic that goes out of our outports. The backbone not being a net generator or consumer of traffic, the numbers track very closely with each other, and they're not double counted. So this is a single counting of traffic. So as Randy said, software to make our routers better will not help, because as you can see, most of our tickets happen to be generated on days when the engineers are in the office. On Saturday and Sunday, when everybody's at home, we have 10 tickets a day. On Monday and Friday, we have almost 3 times the amount. This is data from last month's ticket. This tracks pretty much quarter over quarter, month over month in the exact same thing. So adding a whole bunch of more software to help us be more reliable, unless we can fire all the engineers, it's not going to help us be more reliable. So here's the mythical 5 nines that Dave spoke about earlier. And this is a normalized management view. Out of the types of maintenance we have, 49, 51% breakdown. Almost all the maintenances were completed without impact, and the ones that were completed with impact were the ones that were bollocksed up by the engineers. Even though we have a change management procedure in place, still you can't prevent fat fingering. We are actively working on getting automated config generation, automated sanity checking of our routers. But right now, if an engineer fat fingers a loopback address in your IBGP mesh, you will bollocks up your network, no matter how hitless restart code you have in the control plane. So here's jitter. This is from Frankfurt to Honolulu. For the most part, the jitter is 5 milliseconds. which is acceptable for. And the little spikes you see are circuit flaps as the IGP reroutes around a circuit off the SPF tree. Ashburn to LA, so that's the other way across the country. There's a little bit of missing data because one of our engineers during the maintenance managed to turn off the finger port. You can't make this stuff up. So here's the actual traffic growth, single counted, all our interfaces. This is the average. This is not the 95th percentile. The 95th percentile peaks higher. So for essentially October of last year to October of today, the ATDM went from about 25 gigabits of traffic carried to approximately 80. That's the average. And here's the 95th percentile rate of growth. The missing data is because I managed to bollocks up the little grapher here. But you can see that the traffic growth, the in and out average and 95th percentile, track pretty close. So we managed to make all this backbone work while increasing traffic almost 3 times in 1 year, offered load, and kept maintaining these jitter and latency statistics. So despite our best efforts to bollocks up everything, for example here, it still works. I mean, so that's pretty much all I had to say, except Paul said that he would give me some money if I use the word fiber glut and bandwidth glut. So, well, there they are. Thank you.
The thing is that this is MacBook.
Just like this. Okay, so my plan about having the panelists discuss, for a few minutes what they think about, being a panel and all of that, about the previous panelist comments is not working. So here's what I propose. If we can take a couple of questions in between, if anybody has any for either Randy, Vijay, or myself, or cumulatively. So are there any questions or any comments right now? Oh, good. See, we're showing we're flexible up here. We're flexible out here. Got into the plumbing, electricity, stuff like that. Go ahead.
All right. And Austin Schutz from Clue Crossing. I just had a comment regarding MPLS and complexity. There are certain times when you have more traffic trying to get out of Philadelphia than you can handle, and the union is not being very cooperative in adding lines. But sometimes you need extra tools in order to work around these added complexities that are difficult to solve by adding bandwidth.
That's what I call it, that's what I differentiate the tactical use of MPLS as opposed to strategic use of MPLS. And I think that's one of the things you can do with it. And until we fix the routing protocols in a reasonable way, yeah, that doesn't mean, pour Kool-Aid all over your entire network.
My question is, this is a great topic, and I've loved everything I've seen. What do you kind of hope to get out of presenting it here? Money from me. I've got no money.
It's a good question. We're trying something different at NANOG. It's sort of a socialization, awareness-raising thing, and we need all the minds of all the people in our community to help us work on this, including yours. So I think that's what I hope to get out of it.
Well, I'm on the IESG and I have to read all those internet drafts. So I'm hoping to reduce that complexity metric. No, seriously. There are trade-offs. We're engineers. There are trade-offs in both directions. As the previous person at that mic, there are times when you want something, there are times when you don't. And what I think I'm trying to say is, what I got out of Dave was, hey, there's a curve here, and we should be aware of where we're on it, and where the benefits are, and where the long-term costs are, and what the lessons we can take from others' experiences to try to get 80% of the benefits for 20% of the costs. And remember, I'm just an extremist and a bozo, so, we just needed a little humor.
Extremist. I want to say one thing about the provisioning and MPLS thing, and then I'll let Lisa go. I hope I didn't break your thing. Okay. So I tried to draw this graph for somebody once, but basically, if you look at the green curve, imagine that's the curve of time versus bandwidth provisioning versus time, and let the red one. Don't worry about the scale or anything like that. Just imagine that the bandwidth demand is growing faster than the time it takes you to provision that. That means that you have to get out in front of that curve by, just take a point in time, draw a line straight down, and then draw the lines across from the green and the red curve. And what you realize is that you have to be over provisioned by that much at all times. Otherwise you're going to wind up not being able to carry the traffic that your customers want you to. So you have to start understanding that. And I understand that if you're not a facility-based provider or whatever, that's difficult to do, but it's difficult to do even if you are. So you're always going to wind up being over provisioned by that much, whatever the shapes of those curves are. That's the point I want to make about that.
So maybe I can add to that. As Global Crossing, we definitely run MPLS, and it proves to be a kind of cyclic process. So there are moments in time where you really need it and you're lagging behind on bandwidth, and not over the whole network, but in specific spots. And then for a long time it goes away, and you could actually do without MPLS. But it's so once in a while when you really need it and you have it deployed, it fixes a lot of problems. And there are all kinds of good ideas out there, like IGP optimization, which might hold a lot of value for the future, but the MPLS traffic engineering is something we've been doing since 1999, and other solutions were not available. And we will always be looking on how to do things better, but for now the MPLS really works out in these kind of hotspots and temporary situations.
I think we're running a little late, so I'll be very quick. And as Randy said earlier, this is kind of late of the day and we need some humor, so my talk is not very serious, although I wear a professor's title. So I really think the title of the subject, should be changed. I was going to talk about complexity and network resilience. I think that should be changed to complexity, attacking, and network resilience. And I look at this title, I thought I should rewrite it, something like that, because currently I think the desire to having more and more protocols into a box is overwhelming and not equal weight of the worrying about resilience. Has exhibited an effect to counter-argue or push back the complexity part. What's the resilience? Basically, I look at the dictionary. This is what my this OS 10 dictionary told me, that there's an ability to recover quickly, so I thought I would draw some pictures. So think this is a network, not just a single box. A single box is a very limited power and how reliable it can be, but with lots of boxes together, you can do much better. You get a attack, you get blow, but you can recover from it. That's the resilience. It doesn't mean that you don't have problems, but you can recover from it. You get hammered, you come down, you can bounce up. And how you learn, and next time you get hammered, you're not going to die again, right? That's the resilience. You got a box. What are you going to do with the box? You have to take it out, but I run out of time to do the animation next time.
Use the hammer.
Right. I learned this word a lot this morning about high availability. So what's the resilience and high availability relationship? So here I think is the relationship. On the road, you decide where you're going to go. You want to go to the end, which is the high availability. That's how the ISPs get paid for money, right? But how do you get there? Then you need the resilience and adequate capacity. That's it. Then you get there. High availability by itself, it's not something. You need to learn how to be resilient, like the previous picture showed. Of course, it goes the other way, it's a dead end. For the system like the internet, that's so big, it's so complex. False is just a given, deal with it. And therefore, the real question is not whether you have problems. The question is really how well you can deal with it. And here's the hypothesis that I'm going to prove for you. That is to say that the more complex the system, the less likely you can cope with the problems. The problems, as I said already, will be there. The complexity is defined by the number of pieces. Specifically, I do protocol design, so we'll talk about the number of protocols you have in your box. So how do you prove it? Being a professor, I can write equations. But given that I only have 5 minutes, I'll burn 3, so let's forget equation proof. I'll do something more illustrative, okay? This is the thing. Dave mentioned, I built this thing out of the last 8 years, and to be simple, I only pick one IETF per year. It's a sprint IETF, okay? I'm going to give you 4 lines. The first one is the number of new working groups. I should have drawn the number of total working groups. Then that will not be linear. It will be, going up. Will not be flat. So the new working groups, you can see that every IETF, some number of new working groups gets created. And you know that two are very productive. So for each working group, there is some X number of internet drafts, and correspondingly, the new protocol design, the new RFC is published. So this is the green triangle. I don't know if it shows up there well. That's the new protocol actions. And then this blue cloud, that's the new RFCs published. But let's look at the internet draft. And remember that I put there, I said that because out of scale, so I have to use it times 10. Therefore, anything above 100 is really 1,000. So by the spring this year, this is how many internet drafts we published. I just took a quick look where we're sitting here. For the last IETF, Yokohama, there's 1,200. Although, there's old ones, but think about the new ones, 500 something. Of course, you can say that not all the internet drafts get into your box, right? A lot of them just really not very high quality, so they get filtered out. Like Randy, spending all his weekends reading the IETF drafts, and I think he killed a bunch of them, I'm pretty sure. But the fact is that some do make into your boxes. As a matter of fact, lots of that actually make into the box. I don't build the routers. I have to beg my friend who built the routers, this Fred Baker and Frank Kazenholz and Kirk Partridge. They provide us this list of things. And by the way, this is not a complete list because my screen is not big enough. You can see that I reduced the font as small as you cannot even read it, but it overflows my screen. There's how many protocols into your box. And by the way, this is probably very incomplete because, I asked them 3 a.m. this morning, and they just pump. That's how many they typed. So now we said about how complex, how many pieces of protocol in your current router is currently running on the backbone, and you think that this resilience, right? So since that I declared that the errors are given, how are you going to get the resilience? 3 steps, very easy. Being a professor, you have to be systematic. The first thing is you have to minimize the chances of having a problem. Although you're going to have problems, but you want to have as fewer as possible. And the second is that you have to detect it. And the third is you have to recover from it. Now, I have to combine this slide with what I said earlier. That is, we are very productive. We produce lots of RFCs with lots of internet protocols. How that helps us with the 3 steps to resilience? Doesn't help. They go to the other direction. The more pieces, more way to fail. I wish I had a nice example, but I just quoted this next thing out of the book I really liked. It's called The Secrets and Lies About the Digital something. But here, fundamentally, it says that if for any modern, large, complex code, there are just too many places. Imagine this specific thing about where buffer overflows are possible. The things I really like you to remember is the ones I highlighted out. It says that it's very difficult to guarantee that there are no overflow problems, even if you take the time to check. And think about how many of us actually take time to check about the buffer overflows. That's how all these viruses, get a room to live and to grow and fly. The same thing comes out of bugs. You know, as the lines of code grows, you get more bugs. And I don't even want to mention about potential feature interactions. That's what the previous equation I want to show you. That decides that, you know, as the number of components in the system grows, this interaction actually grows exponentially. And the second step to resilience is that you have to detect the problem, right? But with software, it's very difficult. We had a meeting yesterday for some different thing, and we were talking about this Usenet outage a couple of weeks ago. Why it took so long to actually to fix it? Because the system is so large. It's hard to single points which one is still spreading the bad things. Okay, 5 minutes. I got to go. I really like this talk earlier by Sanjay talking about, you know, there's a fundamental difference between software and hardware. We're talking about protocols, so the software side. You know, he listed some characteristics of the software. I just want to add 3 more onto that list. For one, the reliability goes down super linearly with the line of code. And not only software does not degrade, the bugs do not degrade either. You know, over time they still stay, they don't wear out. And then software is a lot easier to attack. You see software failures are due to the design and user errors. That's also due to the attacks. You know, somewhere from China, I don't know how many thousand miles away, they can easily attack your box, but they cannot attack the hardware per se. So talk about the fixes. There's a third step to resilience. That is, whenever you have a problem, fortunately, if you detect it, you have to fix it. You know, I started learning about TCP/IPs over 20-some plus years ago. In those days, if there was a problem, there was a failure, we thought that the dynamic routing going to fix it. But today, it's no longer the case. Look at the list of all these new protocols and now to handle failure. Not the routing anymore, because there's MPLS, which is different. They need a separate, what's it called, the framework for MPLS-based recovery is beyond, in addition to what your dynamic routing protocol do, then you have to do this thing, and you have the MPLS loop prevention mechanisms, and you have this fault tolerance for LDAP, the LDP, because, you know, there's a fight between RCP-based thing and LDP-based thing. I don't want to mention the company stuff. Not only you have the BGP, graceful restart, and then you have LDP, graceful restart. In addition, once you have all of the new protocols, you have to manage them, right? So there's all these accessories, you know, memes and this and that. And what you end up is something like very different. We already said earlier that how wonderful packet switches and how bad the circuit switches. I have to back the difference. That is, people think differently now because the internet is not reliable. As we speak, you know, today and tomorrow, there is a separate technical conference going on in Atlanta, I believe, called HotNet, Hot Topics in Networking Research. And this is the title of one of the papers we presented there. What the paper says, I quoted something. It says that if you look at, for simplicity, like Randy declared, we can just well look at the, you know, how circuit switch the boxes compare with packet switch boxes. The software running in a typical transport switch for circuit switch is about 3 million lines of code, okay? Whereas the LOS is 8 million. And they quoted from some authority, which, of course, I don't know. That was eye-opening to see this. So which one is more complex? At the moment, the numbers talks. So therefore, the paper said routers have this reputation of being unreliable, crashing frequently, and take a long time to restart. So we're working so hard, adding so many protocols. We are adding the power to this grand, powerful routers. You know, you make lots of RFCs and eventually get into the box. But if you ask the question very hard, you say, do you really add the power to the box or add the danger? You peel off the thing and look what you're adding on. There's lots of pieces piled together. If I peel off another layer, think about it's even uglier. yesterday I had a chat with Van Jacobson, and he was talking about that, if you design a new thing, you can just throw it over. You don't have to smell the garbage, because the garbage can smell it, and you don't want to get even close to it. You don't have to understand it. You don't have a problem, you throw the patch to it, then you go one step further away from the garbage, then you just throw more and more and more pieces. And think that whole thing can be resilient, right? Every piece you throw in is like you hammer the whole system, so it's not making it more resilient, but getting worse. Somebody asked the question of what's the message here. This is my message, that is that we have to put the resilience of the system to a high priority and counter the complexity into a fixed degree. How to do that? It's difficult. It's research, right? That's how I'm paid for. There are lots of things I'm going to learn from you people what we can do to increase resilience and reduce the complexity. But the one thing I have identified is you have to identify the protocols and throw it out so that they make fewer pieces in the box, and hopefully there are fewer box and everything gets dropped. And I believe that this is really the biggest challenge, at least for research. Thank you.
Okay, we're running just a little over, so hold on to your questions if you have them. Okay, so we'll take a question if anybody has one.
Hello, my name is David Ward. I am the token vendor. I work on software and love it. I build routing protocols, and so I kind of feel like the drug dealer up here. And so I took the two topics of control plane philosophies and layering of control planes, and I kind of reworked it a little bit, which came up with a talk of why control planes are built the way they are and how they're being used, and I guess it will be a completely different perspective because I'm not very funny either. So what makes this also complex? Well, basically, the multi-technology network, of course, is viewed as a stack of single-layered networks. The vendors at the different layers don't talk to each other really too much. We all kind of look at our own different devices that we're using and kind of see them in different, or the different devices that we build as different layers and having all completely different properties, not necessarily attempting to unify this all together in all cases. Of course, this is going to definitely lead to a contention between the different single-layer schemes, of course, which is primarily the lack of sharing of spare resources between these layers, and we'll take a look at the cost in a little bit. Another thing that's added to the complexity from our point of view is that there are a lot of new, due to natural evolution of technology, as you would imagine, have created new survivable layers and restoration techniques that are available to us to present to you. Of course, then we have the problem of the different service reliability requirements that you want to offer to your customers and are asking us to build into the devices to allow you to sell those to your customers, right? So we have to worry about those who want to restore traffic at the injection layer, the granularity of the recovery scheme, and providing this across multiple layers inside the network as well as inside the device, and understand a bit the difference between what's going to happen with a lower layer failure versus higher layer failures and how that's going to demand a different recovery. So I'm going to focus a bit on, as I go forward, on the difference between a lower layer recovery scheme and a higher layer one in a few slides. So restoration basics. From a software point of view, at the different layers, everybody's kind of looking at the same problem. And the problem is there's a fault, you got to detect it. There's spare capacity built into the network somewhere. You have to have a router switch to put the failed service on the capacity, and you have to have control protocols to reroute failed circuits. At the highest level, that's really what all of the control plane mechanisms are trying to do. So what becomes interesting, and what's going to come back as a recurring theme in this talk, is the notion of the different techniques, whether you're looking at the lowest layer, the highest layer, or a converged restoration control plane, is the effect of the topology of the network, and the control plane and the layer in which you want to protect and restore traffic is going to determine the amount of capacity you have to overbuild into the network at the different points, obviously. And you can see by the meshiness or connectedness of the network, it's going to rapidly determine how well or how cost-effective your scheme is going to be. Now, of course, you get, as you would kind of imagine, up the higher layers where you get to very meshy connectedness and the amount of capacity overbuild reduces dramatically. So this slide represents the problem, or the one set of a stack of problems. As I mentioned, there's a multi-layered stack of individual schemes that we have to deal with when trying to build networks. Everything from the WDM all the way up to BGP, we've defined at every layer all sorts of little neat hooks and tricks that we can do at each one to restore the traffic at these different levels, because everyone who's building a network has chosen a different scheme based upon the technology or whatever the case is on how they want to build a network and where they want it to occur. Sorry about that. So one scheme is building a network out of boxes, or protection at the lowest layer. So what you're trying to do in this particular mechanism, and it's really fairly straightforward, is that you're attempting to restore traffic primarily at the layer in which is injected into the network. So what this means is that you're attempting to control each specific layer that's not activated for a particular failure and make sure that it's resolved at the proper layer. Now the problem is that anything that happens at a higher layer, other than the one you're trying to recover, doesn't really understand what kind of problem there was, of course. Just don't really know. All it knows is that there's a problem somewhere, take an action and go. So generally what happens when you have multi-layer activation in this particular case, which happens frequently, right? You set your carrier delay on your SONET, you check you set your P&I, you set your MPLS timers, whatever the case is, your layer 3 routing protocols, and what happens is that if multi-layer activation occurs, you immediately get into competition for the network resources, of course. And so at this particular point, the way the networks have built is that you've kind of worked out such that only the devices at the highest layer really are able to control a number of these different layers, because it's the only place where they actually converge. So what becomes interesting is that if you do get the multi-layer activation, as we've all seen, you kind of get the flap and burn scenario where links are coming up, they're going down, they're back up again. It was just a very quick transit failure, and better known as flap and burn. So also what happens when you build boxes or build networks out of boxes from the lowest layer is that spare resources are required in every layer, wherever the recovery scheme is trying to be implemented. And then, of course, if you decide to choose that your recovery scheme is going to be quite high up the stack, the spare capacity pool of all the layers below it, of course, also have to be overbuilt, which can cost a serious amount of resources, as I mentioned. So, putting this on the head, you can build networks out of encapsulations, as I call it, or protection at the highest layer, where what you're trying to do is shoot for absolutely the highest layer in which you know that your service will be guaranteed, and attempting to resolve any problem that occurs underneath it. And frequently, I think as Randy mentioned, this would basically allow layer 3 routing to handle any particular failure below it, whether it's WDM or any other circuit, depending on how the network is being built. Operationally, the complexity can be avoided in this particular case. And you also have finer grained control over the type of restoration you want to do, because you have the ability to control at a much more granular layer. But it doesn't imply that the highest layer recovery is always the cheapest. A couple disadvantages, of course, is that in the event of lower layer failures and how they may occur, you can definitely complicate the rerouting depending again on the granularity in which you want to attempt to restore. You can see lots of networks just independently flapping all over the place, and you have multiple parallel attempts at the different nodes to actually restore the network. Of course, when you're trying to build a network out of encapsulations, you may end up having to go out and reconfigure network elements that are far away from the original failure, or of course far away in the network layer, meaning that you have to go out and reprovision WDM, and there's no other solution to this particular problem because that's your only circuit that's up. So there's been some precautions built into other control planes. An example is, by aggregating LSPs. So that way, instead of handling the complications of the rerouting of all these different LSPs across different ones, you can aggregate them into, say, a bundle or into one representative LSP and just recover that one and have everything contained within go with it. So what becomes interesting is that this also requires a very high degree of engineering, as you have to make sure that the spare and working resources are physically disjoint, and everybody has gotten caught in this trap trying to work at this layer where you think that everything's disjoint, but it's really not. So generally, you can create a higher capacity requirement. So then the third one is converged restoration strategy, right? These have come and gone with the wind over the decades, but at the same time we continue to attempt to come back to this idea because theoretically and potentially even practically from an operational point of view, it appears that there's fruit or there could be fruit in this particular approach. And what you try and do is, of course, attempt to recover disrupted traffic at different layers, and GMPLS is the current attempt at converging the restoration strategy. It supposedly is going to ease operation because we can control switches, we can potentially control WDM equipment, we can control routers, etc. And what we can try and do is recover multiple layers in parallel at the same time. Whether it's IP going in one direction, we can do that. If it's switches and create new optical channels, we can do that as well. But it, of course, is incredibly complex to try and build this control plane. It's also very, very difficult to build equipment because all equipment has to be engineered across the multiple vendor space to react the same way, be engineered the same way, follow the exact same rules, as well as from a hardware point of view, from a system point of view, from a control point of view, everything has to be lined up exactly perfectly across multiple vendors and multiple devices in multiple POPs, of course. Now, what generally we've seen in attempts at doing converged restoration strategy is that you have multiple forklifts at these different layers of the network to bring this equipment actually in, which can be quite expensive depending on where we are in the bubble curve. So the chief complaint of control planes, chief complaint of control planes is really that they compete with each other, and there has to be proper engineering of hysteresis between these control planes, whether you're doing it yourself from the lowest layer up, or it's a converged strategy, or the highest layer down. And the example is that if there's an instant response to level 1 alarms and routers, we could have unnecessary routing activity, routing instability, or congestion if instead that alarm was suppressed. As you can see in the example here, that the link was down for a very short period of time. But if you take a look at what happens with layer 3, the actual recovery from that link, not necessarily even discussing whether or not route flaps or route dampening is involved, it's quite a bit longer than if just a lower layer took control of this. But at the same time, it all depends what you're trying to accomplish. With respect to the cost and economics of choosing restoration strategies, the main point that I want to bring across here is depending on the proportion of traffic you want to restore and how quickly you want to restore it will be directly related to how much you are going to have to spend looking across the vendor space, whether you're looking at all the traffic or in a lambda or a particular LSP or a particular prefix. You really need to choose how much you want to spend based upon the granularity that you want to attempt to provide to your customers. Taking a look at some of the restoration characteristics, the cost of gigabit per dollar is lowest when you go all the way down to the fiber, of course, because there's potentially the least amount of equipment required to move from one fiber to another, depending on where it is on the network, of course. And the highest is probably at the higher layer, or has been shown to be at the highest layer. But you again get to see in the granularity in the middle column there that the finest level of restoration that you can do. So if you have one particular customer and you want to keep them up, you can actually engineer the network to potentially focus just on the granularity that you want. And there's some more data, and you can take a look in your free time on this. So really, you take a number of the pieces that you have in the equation that are facing the way you built your network, cost of service you want to provide, failures, capacity, cost, et cetera, toss this in your planning framework. You can take a look at the single layer protection, and then it pretty much comes out in the cost that you want to provide, and I'm going to come to a summary in a second. But first, talking about the granularity, and you say, well, geez, it looked relatively cheaper on the graph that you had before to take a look at the lambdas. Well, the problem is that there's so much traffic going through a 192 or 48 that it might not be at the level that you want to restore. So there's a big trade-off there. Over to GMPLS, and just a couple of notes that it really is the most modern technique in attempting to converge restoration between IP and optical layers, which is really different than what was tried to be accomplished in ATM or in OSI CLNS networking. But there are a number of challenges in front of us, including not only the deployment and the adoption of the technology, but actually successfully accomplishing the coordination between the layers. And it's yet to be seen whether or not this is going to, again, bear fruit or turn into another significant challenge. So my advice is to remain calm at all times, because even with a level of complexity, looking at either top-down or bottom-up, many networks do continue to function. And of course, the question that Dave's asking, is there a limit to the complexity after which we can't manage it, can't afford the cost, can devices, protocols, and networks be engineered? But my real takeaway that I would have is it only makes sense to pay for an engineer the level of restoration you require, which is, do you really need less than 50 milliseconds? Do you really need 100 milliseconds? Whatever level of service it is that is trying to be accomplished, there is a set of control plane tools, there is a set of devices, and there is a layer at which that can be engineered that a network can be shown to survive. I'm done here.
We can try taking one question if there is one. No?
On point, when you talk about layer 3 heating and that it takes a fair bit of control over, there's of course the work of Thorup, Rexford et al. On minimizing the number of changes you actually, pre-calculating your network for a vast array of failures, and therefore configuring the network to take the minimum number of changes in case of failure, and the paper essentially says, 1, 2, 3 changes.
I agree. There's a number of techniques that can be done in IP routing, and there's some excellent research being done now on both IP fast restoration or fast reroute, as well as how to optimize the network and layout of IGP metrics and different BGP attributes, such that you can come within a very close percentage of what is considered theoretically optimal, and like in the paper that you just cited.
Okay, few slides whether we do or don't need quality of service or class of service in backbone networks. So first, let's take a look at the potential drivers for deploying quality of service in the backbone. I think you can split it out in two parts. One is the application requirements, and the other one are economical. So on the application level, to support things like voice over IP, video, interactive applications, or even worse, PBXs, which need timing over the network, etc. You need to make sure that jitter, delay, etc. are bound to certain values which are applicable to the application. On the other side, on the economical side, the traffic on your network might not all have the same economical value. If you transport long-distance voice traffic, like trunking between switches over your network and internet traffic, the penalties on dropping one class versus the other might be a huge difference. So, on the other side, the concerns. So, what happens to scalability? Can we deploy things on the network which need per state, per session state, or can we afford to deploy classes? What are the limits we can do in scalability? And of course, the manageability, like how much more complex do we make the network for troubleshooting by deploying several classes of service? Then the edge versus the core, which is a complete different view on what needs to happen. So the first assumptions are the core of the network is congestion free, and Vijay has already referred to that. I talked about it earlier today. You don't expect in normal operation any packet drops in the network, even not if a single link fails. But things still can happen. I mean, I would wonder how many ISPs here can claim that they never see any packet loss in the network. I think that number would be 0. But on the other hand, of the edge of the network, the situation is completely different. Here, you interface to customers. There are economical reasons why bandwidth can be limited because they just don't want to pay anymore. Or capacity could be so small, like a T1, that when you want to do any delay jitter sensitive applications, you do need to prioritize. But we're talking about the core here. So for the edge, there is a clear reason why DipServe or similar type of technology would be needed. Also, the per session state, even there would not be a huge problem because the amount of aggregation you do there is really small. But the question is, why do we need it in the core if already other presentations have shown that the quality is perfect anyhow? So again, the over-provisioning is the key to the quality of service. The links are all high speed, so the buffering because of the propagation delay is and the serialization delay is all minimal. That's not an issue, and you can get to high utilization without any queuing. But then failures do happen, and networks are not built for congestion, and when you talk about quality of service or diff server class of service, people easily think that you want to build a network to be in a permanent state of congestion and then do any kind of prioritization, and that's not at all what we're after here. Still, over-provisioning is the key, but the question is, how far do you want to go to prevent yourself from multiple link failures, multiple router failures, a complete site that goes out through a disaster or whatever? So when you don't do any differentiation in the core, what happens is all the traffic ends up in one class. And that means that whatever the requirement is, the most strict requirement for traffic that ends up in that one class becomes a requirement for the whole network. So if you do, I think long distance voice is a good example, trunking between real long distance TDM voice switches, that's not traffic you want to drop for a few hours because it would affect thousands of residential or business users on the phone. It's really different from internet traffic. You can live with some degradation in your internet performance for some time, but not with real long distance voice traffic. So that all comes back to the deployment of quality of service in the backbone is not about affecting jitter, delay, etc. It's about isolation of traffic which has different requirements than other traffic. So it's about availability of certain classes in the backbone. A simple example here, suppose you have a traffic mix on your network with about 20% voice over IP and 80% internet. And the rule to build your network is no link should have more than 50% link load. So in general, you could survive a single link failure because traffic would reroute and links already are at the maximum at 50, another 50 comes on top of that and you would end up around 100. So without any quality of service, everything runs fine for a single link failure. You can survive that and your voice over IP traffic would not be affected in any way. But with quality of service and just a simple two-class deployment with a priority queue and a best effort class, you could go up to much more failures before your voice traffic starts being affected. Maybe up to 5, it depends a bit on the topology, it's not really a one-to-one mapping. But you protect your traffic which has more economical interest to you from other traffic. And again, I keep repeating this, the goal is not to drop traffic, the goal is to transport all the traffic. The question is, where is the point where it goes wrong and how much do you want to invest in complexity to deal with that as well? So another thing to keep in mind when deploying DivServ is keep it as simple as possible. Don't go into all kinds of classes with very complex bandwidth reservations, etc. Make sure you don't deploy any more classes than are real applications. And the other requirement is make sure you don't deploy classes which you cannot distinguish from each other anymore. So to go back to the example I just showed, if you have a class with voice over IP, so there's a clear application for that class, and you put it in a strict priority queue, so it has priority, it can preempt any other type of traffic. You have a clear difference with the traffic which ends up in the best effort queue for the rest of your internet. So what about the complexity? Because that's what we're all talking about here. First, the queuing functionality is available in routers today, so we're not asking here for new features or anything which still needs to go through a lot of development. Also, these mechanisms are supposed to be unused most of the time. So it's not like they're being used for all the traffic all the time, and therefore the risk you hit problems will increase. Make sure that all your marking, so you really, which is much more complicated than just the forwarding, you need to make sure on the edge all the traffic ends up in the right class. That's all done on the edge of the network, so the core has nothing to do with it. Also, this is not a protocol. There's no interaction, no layering, no signaling, etc. It's a completely independent technology from any routing you do on your background. There is an issue though. When you deploy DivServ, really think about how you do buffer allocation. If you make mistakes in there, even with a priority queue and best effort traffic, your best effort traffic might easily starve your priority queue. So it's something to take care of, but not too difficult to do. So what it comes down to is, do we need quality of service in the backbone or class of service in this case? Is yes, but only if you need it. So if you have a good reason, economical or application-wise, you want to protect traffic from failures, isolate traffic from other traffic, it's a good idea to do it. But make sure you only do it on aggregate. So I even didn't mention it because I think it's generally accepted that things like RSVP per session over a backbone are just simply out of question. And So really keep it on the aggregates. Don't go with huge amount of classes, maybe 2, 3, maybe even 4, but I think that's already on the wheelhouse side. And don't do all kinds of complicated policies you can't manage or verify, like on a single port, customer port, start filtering based on port number of applications, put it in a class, etc. There's no way you can track that kind of things and troubleshoot. So really do it on a per service level. So you know where your voice over IP traffic comes into the network, you know where your internet traffic comes in. And make sure that anything which is more specific or complicated stays on the edge of the network and has nothing to do with core routers. And that brings me to the end. Any disagreement on this proposal?
How about general questions on anything that we've discussed? Go ahead. Go, Mike. Go to Mike. If you want to direct it at one of the panelists to do that, or we'll take a whack at it if you like.
This is a question for the last speaker. You talked about having 50% link utilization, and you sort of implied that you could lose one link, but if you lost more than that, you know, your voice quality would rapidly degrade or be non-existent. I don't understand the math. If you've got 50% utilization, one link doesn't necessarily, as long as you've got a backup path for that, you could lose 2 if you've got a backup path to the other one as well. I don't understand how. Were you trying to imply that you would only lose one link?
No, I was not trying to say that when you lose one link, you will have congestion. I was saying that when you lose one link, you could have congestion. There can be scenarios, or actually with one link you would just survive, but we were talking about more than one link. For example, three parallel links across the ocean or something like that. If you lose 2 of them, and you have a 50% load rule, you will definitely congest the remaining one. It becomes more complicated than
But what you're saying is you've got to lose more than 50% before you have a link loss.
You would start losing traffic, not necessarily all the traffic from a link, or is that not okay?
We should just take it offline instead of a question.
Good.
Anyone else?
People with one last.
Okay.
Yeah, I have a comment on the fact that if you have, I know like most networks have more than like 2 to 3 links down at any given point, but if you have 5 link failures that affect a customer, then your capacity planning and provisioning people need to be fired and replaced with better ones.
Oh yeah, that's your algorithm, huh? Yeah, go ahead, please.
My question is actually directed at removing protocols from routers. Which protocols are on the board for termination?
X.25?
IPX?
IPX? There's a long list. There's a long list.
Where can I find that list?
I said that it's a research challenge, so that we have something to do. Actually, I think it's a better thing to do than adding new protocols. When you add a new piece, you don't really understand what's in the box already. That's an easy job to add a new piece. It's a hard job to take out way one, to fully understand the impact.
I once had a programmer, people in my previous lifetimes were foolish enough to ask me to manage people. And an engineer once worked for me, and what I had to say about him before I let him go was, he always added code, he never removed code.
So, along these lines, I would encourage you to uninvent anything that you think you can.
You're right on that.
I've done it a couple of times. It seems to work pretty well.
Come on, Alex.
Alex.
So we're talking about trade-offs between complexity and what we get, what we pay. I was always curious about, do we have any data how much actually people pay for deploying MPLS, upgrading software, getting new tickets, educating personnel, whatever, and how much we gain by being able to defer the panel provisioning decision. So do we have this in mind? I'm just curious.
And don't forget the bugs out of the MPLS release and the outage hours.
Right, so
I'm referring to
has anyone calculated that stuff?
I know people tracking those costs in specific enterprises, but it's not reviewable.
Okay.
Not because it's good or bad, it's just this is very sensitive data inside.
It's kind of one of the problems with this whole thing is that data tends to be proprietary, severely so.
Yeah, I guess maybe, if someone could raise their hand, hey, I'm making money because of that, or hey, I'm losing money. Well, losing money is probably a little difficult, but, just some indication
So
like,
what happens if you don't raise your hand?
well, oh well, I
Anybody
knew
wanna raise
the
their
answer.
I saw something once upon a time, the only people who make money on the internet fast are selling hard drives.
I thought it was porn, actually, but, so, I actually enjoy greatly all the curmudgeonly talk, and it's been my position for some time that there's no job worse than coordinating all the Cisco iOS releases with all the features and all the hardware and all the everything. On the other hand, as a user, having to play iOS roulette when I have, this router with these boards with this software, and I need to figure out which IGP will work with the least bugs with all the stuff that I have to run, it gets tiresome. But I guess the question for the people in the room is, there's a reason why vendors implement all these features, and whether it's graceful restart or NPLS or whatever it is, and why aren't the customers saying, I want a box that routes packets and does BGP and ISIS and these basic things and SSH, and that's what I
That's what
want.
Dave suggested in response to the last question.
Right, so,
Well,
yes, here's what the question is.
Part of the reason for doing this is to raise this kind of awareness amongst all of us so that next time we ask for, what it is we ask for, we think about what the implications of it are.
Okay, I guess if any of the people work at vendors could say, how many ISPs have ever actually said, in terms of requirements, that's the number one thing I'm looking for, is stability, simplicity, and not come with a list of features.
I think they all are saying that right now.
Okay, that's good.
Big John.
We're also definitely getting the request for, we have a very long list of features that are required, and everybody's is different, because everybody makes money a different way. And if everyone was building the same network, then the requirements probably would be very, very simple. But trying to, being the only vendor up there, I guess, we're the only one who can answer it, it's extremely challenging, but there you have it.
John Kahn, Exo Communications. I agree with some of the earlier comments that it takes more work to remove something than to add it, and in fact, it's more elegant to remove. The problem is that we've already got all these out there. There's no admission control. You get a group of people together in a room and they start talking and spitting out internet drafts, and the next thing you know, you've got yourself a protocol. And that gives you more choices and more, gives you a perversity of diversity. I do believe that a lot of us are doing a lot of the same thing, and that we could live with 1/10 the number of protocols we have out there. But that requires that for the ones we do have, not that we go try to hunt them down and kill them, but that we never get those stray protocols in the first place because someone actually did an architecture. Now, a long time ago, I sat on that thing that Randy's on, the ISG, and I said, wow, do we really need 6 protocols to do this, and 5 to do that, and 3 to do this? And as these things came in as internet drafts, I said, we really need to start turning some down, but that requires, again, an architecture. You have to decide, I want this type of recovery in HTTP, and I want this type of recovery in TCP, and I want this type of recovery at each level, and decide what's appropriate and what is overkill and borrowing from one layer too far down. I haven't seen an architecture yet, though, that lets you turn around and turn down the idea, people who come up with a bright idea to reinvent a widget in one more layer than it was yesterday. Have we got an architecture out there somewhere that would help us? That's directed to you, Randy.
I got it.
Okay.
In the IGF culture, there has been change more and more towards that. It is socially difficult, and that is occurring more slowly than hotheads like I would like, but it is occurring, and a good indication of its occurrence was at the last IESG preliminary. I was roundly excoriated from the floor. So if it's hurting somebody, it must be good. I'm just going to leave people with something to read during the rest of this. This is what we don't want to build. Continue. Sorry. I don't mean ever, this is what we don't want to build. Sir.
I'm probably from the other end of Randy. I think that the complexity is just a self-inflicted wound. People want more things all the time. I'm sure that a lot of people can survive with one type of food, but who wants that? And
but we try not to eat foods that interact with each other in our stomachs.
There are still people doing that too, but
less and less of them every day.
but the thing is, when the demand from a lot of different people coming up, and since the problem become more and more complex, the solution need to get more complex to solve those problems. And it will get to a point where when you have way too many things inside the router, and so to solve that problem, people go a bigger router. And it seems like everything seems to be solved with throwing more money, more resources into it. And if problem can be solved with money, it's not a problem, it is an expense. And are we willing to go to that expense to solve those problems or not? And as a job of all of us here is to find the simplest solution to those complex problems. MPLS may or may not be the right solution for this, but it is an attempt to solve those problems. And we may sit here all day and argue that, yeah, it's the right thing, or no, it's not the right thing. But it is an attempt, and until somebody can come up with a better plan, it is one way that people solving it today. ATM, they tried that and didn't work too well. MPLS is another attempt. Maybe it will work, maybe it will not. But that is just one set of solution out of the many, and everybody can come up with a better plan, then that's where everybody will go.
Just to comment on that, I think some of the concern that a lot of us are feeling is that just the premise that you just posited will not be the case. In other words, you'll be dealing with asymptotic upper bounds, and you won't be able to throw enough money and enough compute power at it, and it won't help. I mean, that, and there are several categories of problems that fit that.
Right. Now, but if people can make money by solving those problems in some way, people will still doing that. And in a long time ago, we never thought that the internet gets this big. And it gets this big, and people still throwing money at it. It means that people still think that they have money to be made there. And you may be right, at some point people will refuse to do that, but I don't think we're there yet.
I think most of what, just let me say this one more time, I think the concern that we're facing is a concern about asymptotic complexity, not about the incremental cost of building a bigger box to solve the incrementally larger problem.
And do you see that we are there yet?
People are trying to sell me some god-awful big boxes.
Well, there are examples of things that weren't going to work for day one, like per flow stayed in the core of the network.
I also want to add a comment, which is, you say people will ask for lots of things, but you need to nail down exactly what they are. I went to visit ISP not long ago, and they said, we have to do deep serve, because that's how you can charge the clients differently. I said, why? Doing deep serve, add a whole bunch of filters, this and that. How about you just build a very fast backbone? So they're simple, right? But then they say, how can we charge differently? One way I said is to add some droppers at the edges. For those you charge, $20 per month. It's free, but still keeping the core simple so that whoever pay a big bucks get their reliability.
Sabotage the cheap people's package.
But how you make money is separate thing from how you build the core. I just want to make that point clear.
Martin?
I'm not going to profess that last one. I just want to make a point, which is very simple. In the service provider release of a certain certain vendor's router, and I can't say which one, but I think the number here is 12 dot something. And one of the feature overviews, and I remember seeing this,
That's not my fault.
had to look it up now. No, that's okay. Is that part of this service provider release was the airline product set with MAP IP, which is an airline product set features transport airline protocol data across a TCP/IP network to a mainframe for doing connectivity between agents, set control units, whatever that is, and host airline reservation systems. That code is in X percent of routers running the IP backbone, which wouldn't know an airline reservation from wouldn't know an airline reservation, I think would be the best way to put it. This is an example of either not providing feedback to a vendor, or something just missing from the feedback loop, or whatever. Because that code, if you call a service provider release for use in service provider type networks, there's something disconnected here. The complexity can be controlled. Yes, to the previous question, or the beginning of the previous question, somebody wanted it. No argument with that point, but it wasn't controlled as to who got it. So 8 million lines of code, there's a little bit of more control needed here. That's just an example, as good as one as I can find.
It's a good point. There's just one comment on this whole thread is that there's a question that you might ask, and the question you might want to ask sometime is not whether or not you can, but whether or not you should do some of this stuff, because we get things built all the time because we can, and that goes to the pigs flying and all of that stuff, but frequently we shouldn't.
There are two kinds of design philosophies. There are many, but one interesting to mention is the difference between the intersection philosophy and the union philosophy. The intersection philosophy says do what everybody agrees on, and the union philosophy says throw in whatever anybody asks for. And in today's marketplace, the desire to sell more kit really drives us towards the second. So it's we as consumers, because the router vendors are desperate to sell, because people aren't buying much. So in this situation, if we fear complexity and what it's going to do to our long-term operational expense and our reliability, it's our responsibility to look at that piece of physics and try to be chosen restraint.
Go ahead.
Okay, Andy DeLong, Tunnel Networks. It occurs to me that one of the ways this has been solved in the host world, which one of the earlier speakers who's now on the panel said was somewhat less ticket generating, is by the use of what they call kernel loadable modules for these various features that not everybody agrees on. And if you don't want the feature, you simply don't load the module. Maybe what we need to do is drive the router vendors towards this idea of modular software.
They are. They are doing that.
Ben Black said that.
Yeah.
Yeah, some of them may be doing it at some level, but certainly it could go a whole lot further than it has.
It is.
The other thing, he's right.
Yeah.
The other thing that I wanted to say is there was an earlier comment from one of the presenters on this panel that different vendors aren't talking to each other about the different layers of their equipment. One certain hardware vendor doesn't talk to themselves about the different layers of their equipment and make sure that it works together.
So to Ben's comment on that, I think that monolithic code is sort of a artifact, a historical artifact, and I think modern code is going in the direction you were describing. Go ahead, Ben.
The one comment I wanted to make is that we often see gigantic requirement checklists from certain telco-ish vendors that say, if you do not implement these features, we will not consider your box. Then I wonder when the last time anyone saw a list that said, if you do implement these features, we will not buy your box.
Nice. Yeah. Alex.
Yeah, I just wanted to follow up. So there's there's the software engineering part of the discussion, which is actually pretty easy. You just, have flexible packaging. Well, it's easy for some, not for others. But there's also protocol-related part here. So if, my favorite example is DNS over BGP. You cannot, if you implement it, you're going to have it in a BGP. Do you want to have it? I guess what I'm getting is beware what you ask for, it may be implemented.
Rudiger? No? Okay. Anyone else?
I hear
Going,
this electric blues band.
Going. All right, well, you're in gear, huh? Thank you.